Hi, so today we're going to talk about the action potential in neurons, which is pretty much how a signal travels down the nerve, through the nerve to get to the other side. So first we have to go over potential energy real quick. So the cell is protected and surrounded by a plasma membrane. You know, obviously those are like the outside walls of the house. So the cell's outside walls are the plasma membrane. And outside of the plasma membrane are ions, the sodium ions and chlorine ions, and other stuff, but right now we'll just concentrate on the sodium ions. The sodium ions are positively charged, and there's a lot more sodium ions than there are chlorine ions. So outside of the cell membrane, the plasma membrane, um, is mostly positively charged ions, mostly sodium ions. Now inside of the cell are potassium ions, which are positively charged, but mostly inside of the cell are negatively charged protein particles. So outside of the cell is mostly sodium ions, which are positive. Inside of the cell are mostly negative protein particles. The difference in the charge between the inside and the outside of the cell, so say outside of the cell, there's, you know, there's so much positive charge from the sodium ions, and inside of the cell there's so much negative charge from the protein particles, and the difference between the two results in potential energy, and that potential energy is stored inside the cell's plasma membrane, that divider that divides the inside of the cell from the extracellular space. Since the membrane is in between the two, then the membrane is what holds all of that potential energy from the difference in charges. So the difference in charges between the inside and the outside of the cell results in potential energy stored in the cell's membrane. So let's look at this just real quick. So here is the membrane, the plasma membrane, which protects the cell. It wraps around the cell. So plasma membrane. Of the cell, and like here would be the cell on this side. Here's the inside of the cell, and here would be the outside. This would be the extracellular space. Out here. And in the extracellular space, there are a lot of ions and different things floating around, little floaties. So floaties floating around out here in the extracellular space. Now, some of these floaties are positively charged ions, and the positive charges, they sort of not really magnetized, but because they're positive, because of the charge, they sort of are attracted to right outside the cell, the plasma membrane of the cell, and they line up here. Now inside the cell are a lot of floaties, and a lot of the floaties that are inside of the cell are negatively charged ions. And the negatively charged ions, again, they tend to line up right inside the membrane of the cell because the positive and negatives are attracted to each other. So they sort of attract each other and line up, on either side of the membrane. But the thing is that inside the cell has a lot more negative ions and a negative charge than the outside of the cell in the extracellular space. Here are these positive charged ions. There's a lot more negative charged ions inside of the cell. So that creates a difference. That creates a difference in charge. Now the difference in charge is stored in the plasma membrane of the cell as potential energy. And here's my little pathetic attempt at drawing a lightning bolt so you can get that that's potential energy. Potential energy is all inside the cell. Here's some more PE. All inside the membrane of the cell, excuse me. And the potential energy is created from the difference in the charges, the positive charges outside of the cell and the negative charges inside of the cell. So again, just to refresh, the difference in charge between the inside, which is mostly negative, and the outside, which is mostly positive, of the cell results in potential energy stored in the cell's plasma membrane. So this potential energy is called the membrane potential. Now, membrane potential, it's an actual charge, it's an electrical charge. That's what ions are. So membrane potential is measured in millivolts. Now, when the cell is at rest, this is the setup that I was just telling you about. When the cell is at rest, it's mostly negative inside the cell and it's mostly positive outside of the cell. And if you put those two together, it ends up being the potential energy that's stored in the plasma membrane has a charge of about negative 70 millivolts. And it's negative 70 because there's a lot more negative charge than there is positive charge. And when the cell is just at rest and it has that negative 70 millivolt charge as potential energy inside of the plasma membrane, that's called the resting membrane potential. So let's look at this again a little closer. So here's the plasma membrane of the cell. And here is inside the cell. And here's extracellular space. Now in the extracellular space, remember how I was talking that it has positive ions floating around out there. Now a lot of those positive ions are sodium ions. And a lot of sodium ions float around outside of the cell in the extracellular space. Now inside the cell, remember it's mostly negative floaties. And these negative floaties are proteins. Protein, protein, protein. There's a lot more negatively charged proteins than there are positively charged sodium ions outside. So that ends up making the inside of the cell way more negative than the outside of the cell is positive. Make sense? Now also, just there's a couple of other players in here that I want to point out just to keep in the back of your mind for later. Outside of the cell in the extracellular space, it's not all positive. They do have some negative ions floating around. And those negative ions are chlorine ions. But there's only a few of those. And inside of the cell, there are a few positively charged ions. And those are mostly potassium ions. So there's a few potassium ions inside of the cell that are positively charged. But for the most part, inside of the cell is mostly a negative charge from all of the little floaty proteins floating around that are negatively charged. And the outside of the cell, extracellular space, is mostly positive from the sodium ions floating around. So as we were talking about before, that makes a difference in charge. This is mostly negative, mostly neg. This is mostly positive, mostly pos. So if you add up these charges are measured in millivolts. They're actual electrical charges. That's what ions are. And the amount of negative or positive charge of something, remember the difference in the charges are stored where? In the plasma membrane of the cell as potential energy. And this potential energy is measured in millivolts. And when the cell is undisturbed, or when it's at its default state, when it's not doing anything, it is resting. So we call the resting membrane potential resting because it's not doing anything, just in its normal state. Membrane because it's inside the membrane around the cell. And potential, it's potential energy that it's stored. And the resting membrane potential normally measures out, in a neuron at least, normally measures out at around negative 70 millivolts. Why negative? Because remember, there's way more negative ions inside the cell than there are positive ions outside of the cell. There's just way more negative proteins inside the cell. So it makes it lopsided, so it makes inside the cell mostly negative. So if you were to add up all these negative proteins and subtract it from all these positive sodium ions outside the cell, you would end up with a negative 70 millivolts. And that's a thousandth of a volt. Now, gated channels in the plasma membrane. There's gated channels in the plasma membrane all over cells, but specifically in the axon of the neuron. Now, the axon is the little highway part of the neuron that the signal travels down to get to the other side, to get to the next neuron or wherever it's going. In that axon, the gated channels are called voltage gated channels. And they're called voltage gated channels because they open and close in response to a change in the volts of the membrane potential, of that resting membrane potential of the plasma membrane that we were just talking about. So voltage gated sodium channels, the channels themselves are embedded in the actual membrane. So the membrane, as you go down the membrane, it has little doors that usually remain closed, and some doors are for sodium and some doors are for potassium. The sodium doesn't use the potassium's doors and the potassium doesn't use the sodium doors. They're just the doors are specifically for one ion only each, and they're opened and closed when the resting membrane potential changes, when the membrane potential changes. The resting membrane potential would be negative 70 millivolts. So when it deviates from that negative 70 millivolts, that triggers the voltage gated channels to open up. And they open up at specific times, which we'll go into that in a little bit. But what happens is the sodium channels open up and it lets sodium into the cell. The sodium can pass through the membrane, the little doors in the membrane, and go into the cell. And when all the sodium ions, which are positive, flood into the cell, it changes the cell's charge again. It makes the cell more positive. And since that changes, it changes the membrane potential of the plasma membrane, and the membrane potential goes from negative 70 millivolts and it starts increasing and increasing into the positive millivolts because all of these positive sodium channels are going into the cell. Now, These are the gated channels. Oh, there's also potassium channels that are in the plasma membrane. And after the sodium channels are all done flooding into the cell, then the change in the membrane potential from -70 into a positive number, once it gets up to +30, the sodium channels shut down, the doors close, and the doors for the potassium ions open, and the potassium flows through the channels, through the doors, out of the cell into the extracellular space. Since the potassium is positive and it's flowing out of the cell, that brings the cell back down to more of a negative charge. Now, these all together, these sodium and potassium channels opening and closing and letting the positive ions in and out of the cell, therefore changing the millivolts, changing the voltage in that potential energy, is all involved in the action potential. Now, voltage-gated channels, the ones we were just talking about, the sodium and the potassium, they open and close in response to a change in the membrane potentials measured volts. We just went over that. And this is in the plasma membrane of the axon part of the neuron. So the axon, that tail, or that highway as I like to call it, that's the part that of the neuron that we're talking about. It's in that part of the plasma membrane. So I said that these voltage-gated channels open and close in response to a change in the voltage, right? Well, where does this change in the voltage come from? Well, this change in the voltage comes from two other types of gated channels getting stimulated in a different part of the cell of the neuron. So the mechanical gated channels are kind of all over the place. They're in the sensory receptors, and they're exactly what they say. They're mechanically opened. So like you physically open them. So when you touch your skin, that skin picks up on the pressure of you touching it, and the actual physical pressure that you apply to your skin opens up those channels and lets in other ions to change the charge, the millivolts in the resting membrane potential. There's also chemical gated channels. Chemical gated channels are in the dendrites of the neuron, in the cell body, in the soma. And the dendrites pick up chemicals from other places, and those chemicals are what trigger the channels to open. And when the channels open, of course, the ions flow in and out, and it changes the millivolts of that membrane potential. Now, these gated channels, the mechanical gated channels and the chemical gated channels, they don't change the membrane potential's voltage near as much as the voltage gated channels do. The voltage gated channels are the big player in this, but voltage gated channels can't do anything before a mechanically gated channel or a chemically gated channel gets stimulated. So the chemical gated channel gets stimulated in the dendrites of the neuron. It changes the millivolts a little bit. It makes them go from -70 to about -60. So it only increases it. It makes it a little bit more positive, but not much. This is called the graded potential. Remember how the -70 millivolts is the measurement of the resting membrane potential when the cell's not doing anything? Well, so when the cell is stimulated and these chemical gated channels open up and it changes it from -70 to -60, that is called a graded potential. It's no longer a resting membrane potential, it's a graded membrane potential. So let's look at this in like kind of a graph format, okay? So up here, oops, that was a terrible straight line. This is going to measure the charge measured in millivolts. Okay, so right here, this is going to be -70 millivolts. This is the resting membrane potential. Now, let's see, up here, a little bit further, this is negative 60, and this is called the threshold. And it's called that for a reason. We'll get to that. And then, let's see. Then we have up here is negative 40, and that's not really called anything. It's just negative 40 millivolts. And then way up here at the tippy top is going to be positive 30 millivolts. So what happens is that our resting potential, if you can see down here next to the resting potential, this is where the plasma membrane is normally at when it's at rest, when it's not doing anything. It's just going along at negative 70 millivolts. Okay, now something happens, some sort of charge happens from those other gated channels that I was talking about, the mechanical or chemical gated channels. Those get stimulated and open up a little bit, and that changes the charge amount. It lets in some of the positive ions into the cell, which makes the charge go up a little bit more positive, because some of the positive ions go into the cell, and this is from the, these are from the chemical and mechanical gated channels. Open up, change the charge a little bit, and so it goes up to about negative 60. Now when it does this, between the negative 70 millivolts and the negative 60 millivolts, this is called a graded potential. And I think we went over that a little bit. The graded potential just means it's no longer at rest. It's not at negative 70 anymore. It's going up a little bit more positive, up to negative 60, up to the threshold. That's a graded potential. Actually, this would be over here. Graded potential. Now, once it hits negative 60, it's kind of like a switch flips on. So we'll put a dot here to denote that. The millivolts go up to negative 60. It flips on a switch, and this switch is what activates those voltage gated channels that I was telling you about that lets in all those sodium ions. So the sodium ions move into the cell, making it more and more positive, more and more positive, more and more positive, more sodium ions coming into the cell, more and more positive, until it gets up to positive 30 millivolts. The plasma membrane, the potential energy in the plasma membrane gets up to positive 30 millivolts. After it gets up to positive 30 millivolts, that switch again switches off. The switch flips again, and it switches off. And when it switches off, the sodium gated channels close. So down here, let's see. So down here, the sodium channels open, and it makes the sodium comes into the cell, making it more and more and more and more and more positive. And up here, when it hits 30 millivolts, it automatically, the sodium channels close. So no more sodium, no more positive sodium can come into the cell, making it more positive. So it kind of tops out right there. Now, also, when the sodium channels close, something else happens when the switch is flipped. The sodium channels close, but the potassium channels open. And so the potassium rushes out of the cell. Now, since potassium is positive and the positive potassium ions are leaving the cell, it makes the charge of the cell membrane go back into the negative. So it goes down, more potassium ions leave the cell, taking away some of the positive charge out of the cell until it goes down negative down past 40, negative 40 millivolts, down, down, and then it hits the threshold. Once it gets all the way back down, enough potassium ions have left the cell to make it the plasma membrane potential negative 60 millivolts. Then automatically the potassium channels close. Now when the potassium channels close, it takes a little bit. The potassium channels are kind of slow. Remember I was telling you the channels are kind of like doors in the membrane. So it takes a minute for the door to close. So while the door is closing, some more potassium leaks out, making the cell more negative and more negative, even more negative than its normal resting membrane potential. And then the cell kind of balances itself out. It goes, oops, that was too much. We need to get back up to negative 70. And so it comes back up, balances itself out, and returns back to the resting potential. Okay, if that makes sense. Now let's look at this some more. Right here with the when the sodium channels open, when the voltage of the plasma membrane hits negative 60 millivolts, we can draw just like a dotted line. It's a really sad looking dotted line, but we can draw a dotted line down here until all the way until the millivolts, the sodium channels close, the potassium channels open, the potassium leaves the cell making it negative, and then it gets down to the negative 40 millivolts. When it's returning back down to negative, and it gets down to negative 40 millivolts, we can draw a little dotted line here. Oops. And then the next stage of this is from the negative 40 millivolts, and then it gets more negative and more negative. It goes further beyond the resting membrane potential, a little bit lower than negative 70, down to like negative 80 or negative 90. And then it balances back up at the resting membrane potential. So here's where it balances up at the resting membrane potential. Let's draw another dotted line here at this next stage. All right, now the first stage between these two first dotted lines, when it's going up to positive 30 millivolts all the way back until it gets back down to negative 40 millivolts. This is called the absolute refractory period. The next little section that we drew dotted lines to section off is called the relative refractory period. So you just have to remember the absolute and the relative. Now let's look at this some more. Again, we're going to draw a dotted line starting at that threshold. When it reaches negative 60 millivolts, all the way, and then it goes all the way up until it hits positive 30, and we're going to draw a little dotted line where that happens. So this section right here, from the threshold, when the switch flips until positive 30, when the switch flips again and the sodium channels close and the potassium channels open, this is called depolarization. Depolarization, all it means is when the millivolts, the charge of the membrane potential, is increasing from the threshold up to the maximum, positive 30. All right, now the next section, from positive 30 until the potassium channels close right here, when it gets down to negative 60 again, let's draw a dotted line here. When it's going down right here, this is called repolarization. So repolarization just means when the charge is going from its max, positive 30, all the way down to the threshold again, negative 60. So from negative 60 to positive 30 is depolarization. From positive 30 back down to negative 60 is repolarization. Also, one more thing. Once it hits the threshold, let me find another color here. Once it hits the threshold right here at the beginning, when the voltage gated channels open to start letting in all the sodium, how this is called the graded potential down here, when it's negative 70 up to negative 60, when it's just a little bit more positively charged, that's the graded potential. When it's just resting at negative 70, that's the resting potential. So if those two, or if that's the case, once it hits that negative 60 and the switch flips and it shoots up to way positive, positive 30, that is the action potential. So resting potential is negative 70. A graded potential is greater than negative 70 but less than negative 60. And then the action potential is when the charge is over negative 60, up to negative 30, or up to positive 30, excuse me. So resting potential, graded potential, action potential. And the negative 60 mark in between the graded and the action potential is called the threshold. Oh, I'm sorry, I made a mistake up here. This little sign should be this way. Less than or greater than negative 70 and less than negative 60, if I did that right. Anyway, you get the idea. Now that we've seen the action potential do its thing, just in one space across the plasma membrane, how does this action potential actually travel down the axon? Like, how does the electricity go from one point on the axon and travel actually down it? Well, what happens when the sodium enters the cell, when the voltage gated channel opens up and lets the sodium into the cell? It spreads out. The sodium spreads out. And it spreads out and it's crowded in there, and so they kind of spread out to give each other room, and they spread out in the direction toward where the signal's supposed to be going. So that spreads out down the plasma membrane a little bit. There's too many of them to be in one spot, and so it spreads out a little bit down to the next section of the axon, to the next section of the plasma membrane. So now all of a sudden the plasma membrane next to it has sodium ions and a positive charge, and it's no longer a resting membrane potential at negative 70. It starts going up to negative 60 again. So, and then once negative 60 hits, then that's when all of the voltage gated channels open up in that next part of the axon and that next part of the membrane, and the whole thing starts all over again. Then the sodium ions flow in. It goes from negative 60 all the way up to positive 30, and then that shuts down. It lets the potassium ions out of the cell, which makes it more negative again, and it finally eventually restores it back to the resting membrane potential. Now this traveling from the sodium ions spreading out and going down the axon and doing like a chain reaction. It's cause and effect chain reaction all the way down the axon, so the signal travels all the way down. The traveling itself is called propagation. Now, it's called continuous propagation when it's an unmyelinated axon, when the axon doesn't have that covering of fat around it. It's just continuous. It just travels all the way down the plasma membrane. Now, when the axon is myelinated, when it has those nodes of fat wrapped around the axon, one right after the other, then you're going to be working with what's called saltatory propagation, and instead of the electrical signal just traveling all the way down the axon, it skips from node to node. The nodes are the unmyelinated parts in between the two rolls of fat covering the axon, and so it skips to the unmyelinated parts all the way down the axon. And since it skips over a whole bunch of the axon to travel, but the axon that's covered with myelin, this makes it go faster. So the myelinated axons will transmit the signal a lot faster than unmyelinated axons.